We're still familiarizing ourselves with the basic circuit elements, and now we'll put a capacitor and an inductor in the simplest possible circuit and see how that goes. A state variable is required for each component that stores energy, that is, each capacitor and inductor. So in the circuit shown, we'll have two state variables, one for the capacitor voltage and one for the inductor current. Therefore, we need one differential equation for the rate of change of capacitor voltage and one for the rate of change of inductor current. The capacitor model gives us a differential equation for the rate of change of capacitor voltage, and since the right-hand side doesn't have any non-state variable quantities in it, it is the differential equation we need. The inductor model gives us a differential equation for the rate of change of inductor current. However, the inductor voltage, which appears on the right-hand side of the equation, is not a state variable, so we need to express it in terms of state variables. For this purpose, we can use Kirchoff's law, which tells us that the inductor voltage is the negative of the capacitor voltage, and the capacitor voltage is a state variable, so we're good to go, and we can rewrite the equation as the rate of change of the inductor current equals the negative of the capacitor voltage divided by the inductor inductance. Then we can write the computational equations as shown. The graph shows how the circuit performs when the switch is closed. The current is graphed in red, the capacitor voltage in blue, and the inductor voltage in green. Since the capacitor and the inductor are the only components in the loop, their voltages are mirror images. That is, they sum to 0. So, what happens when the switch closes at time t equals 0? Both the capacitor and the inductor store energy. At time t equals 0, all the energy is in the capacitor and it is fully charged at 5 volts. There is no current in the inductor and no magnetic field around the inductor. When the switch closes, the entire capacitor voltage appears at the inductor terminals. So the inductor sees minus 5 volts and negative current starts flowing in the inductor. By time t equals A, the capacitor has fully discharged and the inductor is seeing its maximum negative current. Now the inductor magnetic field starts collapsing and the negative current continues flowing and charging the capacitor with a negative voltage. By time t equals B, the magnetic field in the inductor has collapsed to 0. By analogy, the turbine has quit spinning and the capacitor has a full negative charge. Now the cycle repeats in the opposite direction. The capacitor negative voltage discharges while positive current increases in the inductor till time C. And then the inductor magnetic field collapses, recharging the capacitor with a positive voltage so that the state at time d is equal in all respects to the state at time t equals 0. And from that point on, the cycle repeats indefinitely. What happens when we add a resistor to the circuit? The same pattern happens, but with the energy in the circuit constantly decreasing due to the current through the resistor. The model and computational equations are basically the same, this time with the inductor voltage equal to the negative of the capacitor voltage plus the resistor voltage, as opposed to the negative of just the capacitor voltage as it was in the previous circuit. I'll leave this slide up for a moment. The graph tells the story. The blue line is the capacitor voltage, and it starts at plus 5 volts and immediately begins decreasing. The red line is the inductor current. It starts at 0, and the negative voltage appearing on its terminals causes negative current to begin flowing. By point A, the voltage across the resistor cancels the capacitor voltage, and the inductor sees 0 volts. At this point, the inductor current begins to drive the circuit as its magnetic field begins to collapse. By point B, the magnetic field in the inductor has fully collapsed, and the capacitor is negatively charged, and the resistor voltage is 0. So the negative capacitor voltage appears as a positive voltage on the inductor terminals, and positive current begins, and so on. A voltage generator is a programmed voltage source. That is, it supplies a time-varying voltage to the circuit that is programmed directly. It can be used to generate a unit impulse, as we will do, or sine waves, or any desired input signal. We can add a voltage signal generator to the circuit. The model and the computational equations are the same as for the previous circuit, this time with the inductor voltage equal to the signal voltage minus the capacitor voltage and the resistor voltage. This graph shows our input signal, the unit impulse. An ideal unit impulse has infinite magnitude and 0 duration, and it integrates to 1. That is, the area under the graph of the unit impulse is 1. So that's the ideal. We'll approximate it with a signal that is 1/100th of a second wide and has a magnitude of 100 so that it integrates to 1, and this code shows how we generate it. Here are some hand calculations you can peruse if you like. Everything is 0 until t equals 1, and in the middle of the screen you'll see at time t equals 1, Vc, capacitor voltage is 0, the current is 0, and the signal at time t equals 1 is 100. Then we calculate by hand the values for t equals 1.01 and 1.02. What happens when the impulse hits the circuit? The graph tells the story. At time t equals 1, the 100-volt signal, which isn't shown, appears on the inductor terminals. The top graph shows the inductor voltage in green. So it spikes up. For 1/100th of a second, the current in the inductor ramps up. At that point, the signal voltage disappears, and from that point on, the circuit acts as a damped oscillator. The bottom graph shows the circuit current in red, the capacitor voltage in blue, and the resistor voltage in magenta, and the inductor voltage from time t.1.01 on in green. Now the magnetic field in the inductor drives the current, charging the capacitor. By point A, the inductor magnetic field has collapsed, and the current is 0. There is 0 voltage on the resistor, and the capacitor is charged, and so on. The assignment is to reproduce the graphs in the video, and it only takes one program to do it.